So hello, welcome back to the session about RF and terahertz application. It's going to be a session of 1 hour and a half in principle, okay, and we'll have several speakers. So Ursula Ebels will make an introductory talk about the applications of RF and terahertz that use spintronic devices. So Ursula and Jon, okay, and Jon, okay. Okay, so Ursula is responsible for the SPINCOM project, okay, and Jon is responsible for the TOAST project, so the project about terahertz applications of spintronics. And then we'll have 3 invited speakers from industry. So we will have Philippe Thadet from TeraView. J'ai rien fait.
Okay, non, ça touche pas.
Yeah. Okay, so we will have three speakers that are invited and come from industry. So we will have Philippe Thadet from TeraView in Cambridge. We'll have Adrien Aubourg from Synthwave-Lasers in Bordeaux. Okay, and Mireille Miron from Golana Computing in Grenoble. I guess I haven't asked. Okay, so please welcome Ursula and Jon.
Yes, thank you very much, Thibaut, for the introduction. And yes, before starting, I just wanted to say you have heard a few things this morning about sensors, and if you think about applications in spintronics, I think most are familiar with magnetic sensors and magnetic memories. But spintronics, as you have perhaps also seen, has many more properties and functionalities. The materials are becoming more and more broader, and lots of more also properties that are discovered in the last years, or 10 years, one can even say. And some of them are microwave and terahertz functionalities that we are going to talk about here. And if you think about this, you can look at the frequency spectrum. And if you think about radio frequency, microwave signals, evidently all of you think immediately about communication because this is the main application, or one of the main application areas. Anything that is going with wireless communication and Internet of Things, smart sensors, RFIDs, RF sensing. You can find a lot of ways and applications using RF signals, RF emitters, RF detectors. And how can we link that to spintronics? We have seen this morning the main component, or one of the standard components, is the magnetic tunnel junctions, where you can spin polarized currents. And then with magnetoresistance, you can read out the magnetic state, but magnetization is something else. Magnetization is an angular momentum. Angular momentum, I guess everybody has been playing with a spinning top. It can precess, okay? So magnetization can precess. It can precess at megahertz to gigahertz frequency. So that is a little bit the link, without going into detail, how and why we are or why this can be of interest for these type of applications, because we can excite and detect these oscillations, particularly when we use ferromagnetic materials. This is in gigahertz. But it's also well known, in order to increase, for instance, data rate, we want to go to higher frequencies, higher throughputs. So one can use anti-ferromagnetic materials because their internal fields exchange coupling is much higher, and that drives the precision to much higher frequencies. But then one can also use other concepts from spintronics, where, for instance, you use a femtosecond pulse to get a terahertz pulse or terahertz radiation out of your system for terahertz emitters. That is just simply to give a very brief indication of the concept, and we are going now to show you a little bit what we are doing within the pepr-spin. And I will start with this. Sorry, I always mess up the SpinCom project that uses these magnetic tunnel junctions. And so here we can basically dissociate or distinguish two types of functionalities. We can generate RF signals, putting a DC current in. With, due to spintronics properties, we can generate RF signals. So these are spintronics oscillators. We can also do the reverse, injecting an RF signal and getting out DC currents. And so like memories and sensors, they have the advantage of being nanoscale. They are CMOS compatible, operate at room temperatures. They can cover actually large frequency range depending on how we engineer these magnetic stacks. We can tune their frequencies. That leads also to something what we call multifunctional, because we also can modulate or can scan the frequencies here or synchronize this. And yes, and we could also think about perhaps reconfiguring. So if you can have several functions in the same stack, one could reconfigure that. Now, what I also wanted to say is, yes, this is a research that is still a bit more basic when we compare it to memories and sensors. So it's still a bit exploratory, even though we also make efforts to go a bit forward, as was mentioned this morning, trying to make proof of concept devices. But I think this meeting here is actually a nice platform to see a little bit, I mean, to expose this to other actors and see whether there is any interest to them for these type of applications. So further on, I mean, for this tunnel junction, I mean, these RF functionalities, the idea within this project SpinCom, as you well know, RF communication is used in lots of everyday type of applications, security tracking, traffic control, and so on. And here the idea is to address issues like power consumption. I mean, using components that lead to lower power consumption, increase the autonomy via energy harvesting, but also addressing the security of data transmission, or more like a classification of signals. That means it's a bit of artificial intelligence type of applications, and you can visualize this in this type of smart sensor networks with the sensor, data processing units, and communication units. And here we can increase the, let's say, not increase, but help the power or reduction of power consumption by generating or creating some wake-up receiver. That means these elements are very power consuming. You would like to switch them off if they are not needed, and then use some low power system to wake them up. And here our devices where we convert RF into DC signals, they can be used as such wake-up receivers. That would be a narrowband kind of application of this, but we can also use them in a broadband way for energy harvesting to power up some components, evidently not the whole system, but there have been first demonstrations to power small components, nano electronic components. And we also have here efforts to do this for a proof of concept using CMOS integration of these devices with the system around to really demonstrate that. And then the second application is what I said, or the type of functionality is the signal generation, the DC to RF. And there is some very nice demonstration where one uses the complex dynamics of coupled system, where one can generate really specific dynamics. Here in one case that is called exceptional point, that can be used for very sensitive threshold sensing. And there are other types of complex dynamics that are used for a random number generation via chaos. I mean, why is this? I have, sorry. So if you look again at our smart sensor network, so that would be more the sensor part, but you also want to make sure that the data you transmit are secure, that they're not read or intercepted by somebody else. And for this, you need to encrypt data. You know that many concepts are based on, let's say, algorithms based on computers that are not 100% secure. But if you know the algorithm, if you know your seed or whatever, you can you can crack it. So what we'd like to do is for the encryption is to use physical processes like chaos or stochastic processes to do this. So we have actions on this, and in the end you could even use these chaotic signals to also for the communication. Instead of having a nice sinusoidal signal, you could use a chaotic signal to transmit. So besides these dynamic effects in such small pillars, one can also use now the propagation effect. That means spin waves. Spin waves is a bit like when you put a stone in a pond, you get waves of it. So in the same way you can generate the waves from these processing moments. It's the phase that is propagating along. And what is kind of nice with these spin waves, that depending on the material combinations, you can really engineer the dispersion curve. That is the frequency as a function of the propagation and propagation direction. Here, these are some examples. But there are also other effects, like nonlinear effects that can lead to 3 and 4 Magnon scattering. So you come in with one spin wave, you can get out with two other spin waves of different frequencies and wave vectors. So these are the strong points. There are also evidently some issues that need to be tackled, something like the lifetime and conversion efficiency when you go from the electrical domain to the spin wave domain. But typical applications, at least for signal processing, so there are others, that is just some examples, would be non-reciprocal devices, so you can transmit in one direction but not in the other direction. You can have frequency conversion, that means you go from one frequency and you split this into several frequencies. One can engineer materials that go to tens of gigahertz, so higher frequencies, and different types of delay lines, adjustable or active delay lines. So it's, I think Thibaut, who would be the expert to afterwards explain questions on that. And then we continue with Jon on the terahertz part, so I'll let him explain this aspect.
Thanks, Ursula. Yeah, so I coordinate this third Moonshot project, which is at higher frequency than what Ursula explained. So the idea is to use spintronics to interact with terahertz wave, to generate terahertz wave, detect them, manipulate them. So this is a bit the, let's say, dream platform we were proposing at the beginning of the project, which is to do a full spin-based terahertz information processing platform. We are pretty far away from that, but the first element that we focused on, and which is, let's say, the most advanced, is the emission part. So here we use a femtosecond optical laser and exciting some heterostructures with magnetic layers, with processes that I won't get into. We are able to generate terahertz emission with some really nice properties. So they have very high bandwidth, they're very easy and simple to fabricate, and we can also embed some modulation schemes that can be quite fast. Then in a more exploratory step, we want to study the interaction between these terahertz and some magnetic materials to try to manipulate the terahertz information. So the advantage here, as Ursula was saying, is that there are some materials that have some magnetic natural dynamics exactly in this frequency range, and so we can use them and the tunability of these magnets to try to filter terahertz information, transmit terahertz information. And finally, we want also to do kind of terahertz to DC down conversion, so be able to have some detectability that we could also tune via the magnetization, potentially with a narrow band detection bandwidth. So the idea is twofold. First, we want to push already the whole field of spintronics into a higher speed regime, into terahertz regime. And for this, we need to study these two interactions. And the second fold, we want to try to bring new solutions for terahertz science and technology by using spin. So maybe the first maybe key application that we envision is the use of this spintronic-based terahertz emitter. So we can categorize the emissions, the terahertz emitters in two types. We have typically single frequency continuous wave emission sources, like, for example, quantum cascade lasers. We also have broadband pulsed emission sources, like that use optical rectification, or we have photoconductive antennas. And the spintronic emitters are exactly in this category, and the advantages of these are the very broadband emission. So this is, for example, the case of the red emission spectrum you see here that covers the whole range from a few terahertz all the way to tens of terahertz. And the advantage is that these films are typically very thin and interact very little with the terahertz. And so we avoid all the possible absorptions of other sources that are typically in this range. So there's already one startup that is selling these kind of emitters in Germany, pepr-spin. And so the advantage of these emitters is that they have the largest bandwidth that we know of all sources. In this, especially, they're very intense in this 5 to 12 terahertz band. They're cheap and easy to fabricate, and as I said, and you can modulate them by just modulating the magnetization. So some of the applications, but I think TeraView will present this much better, that we envision would be that we could use these either for terrestrial communication or maybe more realistically for spectroscopy, for detecting, because in this range we have so much absorption in solids and in molecules, we can use it for fingerprinting different chemicals, for example. It can be used for industrial testing of materials, of thicknesses of layers. So maybe the key highlights in the last couple of years of the groups working in the consortium of this type of emitters has been the enhancement of the emission. So we started with pretty low emissions. And so by using some, for example, some cavity engineering and some antenna engineering, we've been able to increase the output of these emitters by a factor of 10. And now there's a lot of work in the community to try to enhance them by modifying the intrinsic effects, the spintronic effects in these layers to enhance even further the emission. And so right now we are like the state-of-the-art emitters are apparently already competing with other sources like lithium niobate. So we think they're pretty promising. So I think with that, I'm done.
I put up, sorry, yes, the last slide just to, as a summary, just to remind that, yes, we cover, let's say, two broad frequency ranges in the megahertz and gigahertz, terahertz for various type of applications. And so that is, let's say, a few, in some sense, bottom up from the researchers. So what we imagine could be done with these devices, also from what, well, we can know, what we can see from literature, but I mean, it's always good then to present this to more industrials or more applied people and have their feedback and see whether there is anything that could be useful. And with this, I think, Thibaut, you can take over.
Well, except taking the microphone and giving the microphone back. Okay, you don't need a wake-up receiver? Okay, so let's go to the next talk. And please call Philippe. And we'll group the questions at the very end. Wow, there are so many things opened.
It's TeraView.
Second one on top? Yeah.
Right. I'd like to thank the organisers for giving me an opportunity to talk to you today. Everything I'll be talking about today will be done with photoconductive receivers and emitters. So I feel a little bit of a mouse in a field here with all the spintronics, but hopefully it'll give you an experience of what you can do in the terahertz region. Every topic here I can talk for 45 minutes on. Don't worry, I'm not going to talk for 45 minutes because I've got to catch my flight back to the UK. So I'm going to go through, I'm just going to pick one slide from a very large presentation and give you a flavor of what the applications you can do with terahertz. TeraView. We spun out of Toshiba Research and the University of Cambridge a quarter of a century ago, 25 years ago. Interestingly enough, we IPO'd on the Korean stock market last December. So the people who are setting up their own companies, there is a potential future that you're going to get out. When we formed, we were going to be a medical imaging company. We were going to look at things like skin cancer, teeth, but what we quickly realized, that is a very, very difficult area. There is so much documentation, so much regulation in that market. We quickly looked around and we started exploiting other areas. So what we currently work in is in lithium-ion battery inspection, automotive, industrial films, semiconductor, and in the pharmaceutical world. Not only do we have blue chip investors, we also work with a large number of blue chip companies, which are based over the whole of the planet, mainly in the northern hemisphere. But that gives you an indication of the reach of TeraView today. One of the things I'm going to do is try and state an unmet need. So I worked for a couple of years in a medtech company. In a medtech company, you've got to say what your unmet medical need is. I'm trying to extend that to the terahertz. So for what we call EOTPR, EOTPR is electro-optical terahertz pulse reflectometry. There's a need for the AI chips, the inspection of the AI chips, to be able to do something that's fast and accurate. We need to be able to find faults within the package to within a micron, and we need to do that quickly and in complex structures. So what we developed is an instrument that is based on. Oops. Sorry, back. I'm going all over the place. Right. Is an instrument that's based in a unit here. Now, we developed this, back in 2003. Then we started selling it to the semiconductor industry. And because of copy exact with people like Intel, we're not allowed to change what's in this box here. But what's in the box is a short pulse laser. That short pulse laser irradiates our photoconductive emitters and receivers. And what we then do is couple that into a waveguide, which then goes into the device under test. This is the manual system that we got up here, but also what you can do is an automated or a semi-automated system. And if you get any changes in the impedance of the device, you get reflections coming back. They are pulses, and not step changes as you would find in traditional TDR. As I said, I just picked a couple of examples here. Well, actually, one example here. This is case study 6. Most of this community have done current voltage testing, and what we see here is some packages that have undergone the current voltage testing, and the company has set up a test parameter, and all these devices here would pass the test. However, if you look at the terahertz image, the EOTPR signal, this first big spike here, that's the impedance change from the coupling of the device into the radiation into the device. So we get a reflection coming back. That's effectively our time zero. What you see here are reflections coming back from the failure point or the pass point within the device. Here, these are pass. These two here are fail. And these would be embedded in here. They would have passed this test here. But in here, you could see that there are resistive opens. And those resistive opens are due to a small micro crack in the device. Our AI chip at some point would have failed in our phone or in our tablets. So that is the type of things that we're looking for in that. TeraView doesn't talk to the terahertz community about this much. We go to IFSTAFA, which is the failure analysis conference for semiconductors. So you won't hear us talking within the terahertz community or even the spintronics community much about these. I'm going to move something on a totally different scale. There's now a driver, sorry for the pun, that in the automotive industry, we all want our cars to look perfect, but the car industry wants to reduce the amount of paint it puts on the vehicle. But they can't put too little paint on because the paint will come off or be washed off or scratched very easily. So the industry needs a rapid technique of being able to detect the thickness of each of the film thicknesses. Now, the film thicknesses on a vehicle are complex. They're multi-layer structures of a electric coat, a primer, a base coat. The base coat is the color, and then a clear coat, and the clear coat is a protection. And these are all complex, and we have to develop the analysis methods to do it. Again, a lot of the time what we do is spend time completing matrices against all the other competing technologies. And of course, terahertz is going to have all ticks all the way through, but we need to set up our competition, understand the competition. Like here you got photothermal. Basically, you blast the vehicle with some light, and you look at the time it takes for the heat to recover. So you can't see multi-films, but it is a non-contact. It is a non-contact technique. However, the main standard is ultrasound. The ultrasound you've got to couple with liquid, and you've got to put it onto the vehicle. The car industry hate that. It leaves resin stains, so they want something that moves you forward. And these are complex systems. I was asked, would you be able to use lasers in an industrial environment? Well, yes, we do. So this big box here would contain a femtosecond laser. These would be fiber optic links to the robotics. If you are setting up a company, these are the things you'll need to think about, is how you get the units. Sorry about the numbers here, they seem to have gone awry in this particular presentation. And we don't sell to the VWs, the Renaults, the BMWs. We sell to integrators. And then the integrators install this on site. So we're actually one step away. To give you some idea, this is a slide I stole from VW. They gave a presentation at Circar last year. And you can see that they are rolling these things out into their different market sectors. At this conference, VW said that they want to inspect 10% of all their production with terahertz, 10%. The VW group makes 24 million cars a year. So that's 2.4 million cars that they're going to try and inspect with terahertz over the next few years. Why? Well, if you even save a micron of paint, the payback time is very quick when you've got 24 million vehicles in your production. So for them, it's always payback time. A lot of us started getting EV cars. I don't think you realize the amount of electrode that's needed in that. And one of the things that we have realized very recently is that there is an issue of how you monitor the production of the electrodes in the production facility. These things are moving from a few meters per minute up to 20 meters per minute, up to now they're talking about 100, 200 meters per minute. So you've got to have sensors that are working fast. So we're here in the early stages in the electrode procedure, and those of you who drive Teslas or BYDs, you've got somewhere around about 25 kilometers of electrode in your vehicles. I was quite shocked when I saw that number. And again, here is the same matrix that I've shown before. This is a strange one with regular calibrations. We don't need regular calibrations, which is actually a benefit here. So to give you some idea what this looks like, here we've got 2 terahertz sensors. There's an energy chain here. This is 450 millimeters, and the electrode is coming out of the wall. And these sensors would move left to right on both sides of the sensors. An electrode consists of a composite, a current collector, which is usually aluminium or copper, and then another electrode. So we want to monitor both sides of the electrode. This is an example across an electrode. You see this wavy line. What you want is a straight line. The other side 1, side 2, it's almost in anti-sync, so that when you look at the combined layer, it's almost within specification. And the black line is what you see in the micrometer, but you don't see all this microstructure. Terahertz, you're able to get the density, the loading, and the conductivity of the electrode, and all these are important properties to the performance of a battery. Last topic I'm going to just cover briefly is pharmaceutical. Some of you may know that I spent a lot of time looking at coatings on pharmaceutical products. The pharmaceutical industry didn't want to know what their coatings was. However, they do want to know about disintegration. And disintegration is a function of the porosity of a tablet. It's the length of time that the water takes to migrate into the product. So we had a UK government project, and so this is what we're doing a lot of times in the UK, is have small projects that are highly focused on developing something. This big unit was the end of the product. And then you get into the valley of the death. Valley of the death is you want to take that to make it into that, to make it something more commercial. And so usually that's done under your own dollar, euro, whatever. European Union don't like government spending going from the prototype to the final product. And what we do in this one is, it's probably the simplest terahertz measurement you could do. You generate light. Oops, done it again. You generate some light. It goes, if there's no sample, it just propagates through and you've got a pulse. If you've got a fill in there, you've got some porosity caused by the pores, you've got an effective refractive index, you measure the difference between those two, and you're able then to relate that to the porosity. Or if you're clever, you can start relating that to the disintegration time. And what's great here is that you've got here the outliers, and it's the outliers that the pharmaceutical industry are interested in. They don't really care with things that are falling within the trend. And that's work we've done with the University of Cambridge. So, to summarize, what's happening with terahertz? Well, there's an increasing need for performance of analytical instruments. And traditional techniques either don't fit or give an unmet need. So there is an opportunity for us if we can identify those unmet needs within industry. And they also want to be able to inspect in light. Pharmaceutical, no, they don't want to because they're generating millions of tablets. But people like the EV people want to be able to monitor and reduce the amount of waste. And with that, it's not just me, but here's some of the team at TeraView. Thank you for your attention.
Thank you very much. So as I said, we will keep the questions for later, and okay, and so I'll call Adrien Aubourg from Synthwave in Bordeaux. Okay.
Merci. Thank you very much for the introduction. So I am Adrien Aubourg, CEO and founder of the company Synthwave-Lasers. First of all, I would like to thank Vincent Cros for the invitation to talk during this session. He saw some connection between our technology and what you do. So let's find out which one. So first of all, I don't like cliffhangers, so I'm going straight to the point. What we do is, is designing, building, and selling gigahertz laser pulse synthesizer. So basically, they are pulse laser, but with this feature of the gigahertz repetition rate in a very flexible manner. The idea is to synthesize pulses thanks to electro-optics modulation. This gives tunable and flexible laser parameters. So we have a very modular platform with very unique performances. So as you can see, I'm not working especially in spintronics. I'm working mostly in the photonics domain. I'm a laserist, so you can correct me anytime I say some mistakes in your domain. So first of all, Synthwave-Laser is a 2 years company. Almost, but we are built on 10 years of experience. Because on 2014, a first system has been built at LP2N. So LP2N is a laboratory located at the University of Bordeaux. This was the first unit built in the frame of a small grant called avec. And this started some very fruitful other kind of research, mainly around picosecond acoustics, in which there is a patent granted at CNRS. And then in 2016, some research has started around gigahertz burst laser processing. So this is this was a very new way to process materials, so drilling holes or welding materials together. It was so interesting that a few years later, a European project has started called Kilowatt FlexiBurst. In that frame of the project, 2 new units has been built. And then what's interesting today is in 2022, a national grant called GigaSpin has been awarded to LP2N around Brigand spectroscopy and spintronics applications. So I will talk about it later. And so for many years, we had a lot of requests from partners, from industrials or other academics. And so the laboratory decided to found Synthwave-Lasers in order to provide a solution, an industrial solution, which includes this technology to reply to all the requests from the partners. So we are currently in the phase of industrialization and business development right now. So what are the current limitations of the laser source that you can find right now in the commercially available? So all of them, whether they are mode-locked laser or acoustic laser, have fixed specifications. This mostly comes from what we call the optical cavity or the optical oscillator, which induce a lot of constraint on the laser seed specifications, and namely the repetition rate. The repetition rate is limited by the length of the cavity there. So there is no available and commercial solution for versatile and flexible laser source, especially emitting at the gigahertz repetition rate. So how do we generate those laser pulses? So this is done by the electro-optic modulation, thanks to phase modulator and amplitude modulator, and of course electronics and radio frequency components. So we synthesizes the laser pulse with these optical modulations together. So I can describe it a little quite fastly, but we start from CW optical input, so optical laser. So you can see in the time domain, you can see all the optical frequency there. And we do some phase modulation first, then amplitude modulation. And inside this shape, temporal shape, we also have a spectral phase that we can compress to get the pulses. So we can get a continuous train of pulses, or we can also generate bursts of pulses. So in the spectral domain, if you take a laser, an usual laser emitting at a repetition rate of 100 MHz, so in the temporal domain, we get pulses separated by a period of 10 nanoseconds, and in the frequency domain, you will get all the modes there separated as well, longitudinal modes separated as well by 100 MHz. And if we increase the repetition rate, so of course we increase the number of pulses generated in the temporal domain, but we also dispatch the longitudinal mode in the frequency domain. So this gives us access to new apparatus in which we can generate even higher repetition rate. So there are some many unique features of this kind of optical architecture. First of all, the repetition rate can go very high. So I admit that in order to reach 1 terahertz of repetition rate, we need to use additional steps of generation. But typically, we can generate from 1 gigahertz to 20 gigahertz very easily. The pulse duration as well is tunable. So this is tunable during operation, and the same for pulse duration as well. The burst regime and the synchronization of the pulse emission are very easily done, contrary to the usual laser source that you can get. Usually, if you want to synchronize the output of your laser, you have to put a detector and a phase lock loop and some actuator inside the cavity and so on. This is very, very easy in comparison. And one other advantage is the wavelength is not, we are not locked to one or few wavelengths. Actually, we can shift the apparatus as I showed you to any wavelengths. There are some constraints, some conditions, but most wavelengths can be done. We have some requests at 920 nanometers, for instance. Of course, we work in a 1 micron and 1.5, but other wavelengths are also available. So this is important for you because sometimes you need to have precise gaps to excite, and we can address those gaps thanks to a specific wavelengths. So what are the benefits of the technology? So before going directly to spintronic, I will talk about other kind of application. So first one is laser machining. I told you before. In the world of laser machining, they are right now looking at using gigahertz burst laser at a repetition rate of 16 gigahertz or lower, but the important point, it needs to be tuned. And the burst duration should be tuned as well. They need this flexibility actually to adapt the laser parameter to the material being processed. And if we bring those features, and we do, we got some benefits, meaning the ablation rate can be multiplied by a factor of 5 or 10, depending on the material. For quantum technologies, we have some current requests right now that we are addressing. They want to synchronize pulse emission at 3 gigahertz at a specific wavelength of 920 nanometers with a synchronization on a 10 megahertz reference. So this is to increase the current time and generation rate of the qubits. So this these requirements cannot be filled right now by any other kind of laser architecture or any usual laser you can find right now. So this architecture can really address new needs in many different communities. This is the same for photo injections. They need a specific wavelength at a specific repetition rate, always synchronized. So let's go to the first result of ANR gigaspin. Just for you to know, this is a world premiere of this showcase of the results. It hasn't been showed anywhere else before. I just got them yesterday, to be honest. So this is an ANR called Gigaspin in collaboration with LP2M, of course, which bring the laser itself and the apparatus for testings. Institut de Physique de Rennes as well is included. Unité mixte de physique CNRS Thales as well, and laboratoire des sciences et techniques de l'information et la communication de la connaissance. So, what was the point of this project? It was not only to make some measure in terms of Brillouin light scattering or spectroscopy, but also to build a whole instrument and a platform to do this measure in order to test different material the community can come up with. So of course this involves the development of a specific laser source with all the features I told before, and the design and fabrication of ferromagnetic and anti-ferromagnetic films to test, to run the first test. And of course, no, it's not of course, but the apparatus actually is quite the same between Brillouin light scattering and the measure of the spin precession inside the material. So I'm not sure right now that this platform is available yet. I guess it will be soon, but we can talk about it later with Eric Cormier in the audience. So first, I will talk about picosecond acoustic. This was the original idea that pushed the development of this new architecture. So maybe you know the time domain Brillouin spectroscopy, where you have one pump to generate a thermal shock inside the material under test, and then you have your probe that will analyze the shift of the thermal shock inside the material. So you have this kind of measurement in the time domain and in the frequency domain, but this induces actually to have a free space line delay that you need to move, and you have to add up also a lot of measurement because the sensibility is not so great. So the idea at LP2N is to have a very high repetition rate laser that will actually create a reflective index grating inside the material in order to excite resonantly the Brillouin scattering. So actually what we do is not a sweep in time, but it's a sweep in frequency or in the repetition rate of the laser. So you just turn a button and the repetition rate of your laser changes. And you can scan the variation of the reflectivity of the material there to get the Brillouin resonance of the material. So with the same apparatus, there is something else we can do, and most interesting for you, is to look at the frequency of the precession of the spins inside the sample. So I don't have any information on the sample, but I guess you can ask Majib. So yeah, this is really new, that's why. So the idea is to test or to measure the frequency of the resonance of the precession of the spin inside the sample with the same technique. So with this frequency sweep, we measure the frequency of the in which we have the most reflectivity. So again, we need this very specific laser source, which can only be done with the architecture that we developed. So this is really preliminary results, soon to be published, I guess. So here we can see that we measure frequency around 16 gigahertz for the resonance of the spin precession. So in terms of product line, right now we have two products. One we call Neon Flex, which is the modular platform to handle all the requests. So most interesting if you have some very weird requests for me, I can address most of them because this is a very modular platform and we can do a lot of things with that. So of course we have a very small product, let's say, with less feature, but still a really interesting feature comparing to what we can find right now. So it's a simple gigahertz laser source emitting in between 1 and 80 gigahertz at 1.5 or 1 micron. Okay, that's all for me. Thanks.
But the price is not specified. So we thank you, and we go to the last speaker of the session, Mihai.
Hi, good evening. It's very nice to be here. Thank you for inviting me, and I hope to be entertaining and keep you awake for the last talk. So, if by any chance you have questions, don't hesitate to ask during the talk. Right, so I'm Mihai Miron. I used to be part of this community till 3 years ago when I co-founded Golana Computing. And Golana Computing is a startup that does AI also based on magnetism. So what we do now is build an AI assistant that connects to your machines. And when I say your machines, they can be industrial machines, they can be research machines, they can be any kind of machines, mechanical, electrical, anything, cars. So the problem that we solve, let me see if this works. You can see it here, generally for the industry. On the left, you see the ideal picture. Everything works fine, everybody doing promotional videos and pictures only show the best image of their industry. But the real life, as you already know, the same in research, real life is complicated. You have failures, you have breakdowns, you have safety issues, you have human problems. Everything is more full of friction compared to the ideal picture. And this is the kind of problem that we're planning to solve. Now, how do we solve this? And you know that the best way to solve any problem nowadays is use AI. Okay? And this is what happens if you ask ChatGPT a question about the real world. This was on last year, so they have a new version, but I'm not sure it does anything better. The short answer, it doesn't know. It cannot answer what happens in the real world because there's no information about the real world in ChatGPT, I mean the physical world. So now, this is what happens if you ask our system about this kind of information, okay? And it gives you real information about what's going on in the machine. It can tell you about the symptoms of the machine, can help identify the causes, and also help you deciding on the actions which are best suited. But beware, the LLMs have dangers. Because if the LLM is wrong, it's going to be very confident in telling you what is wrong and how to fix it. And in some cases, this can be not just a problem of optimizing or losing some money, but it can be dangerous. It can involve safety issues. So it's really, I mean, the core of the problem is how do we inform LLM correctly about what's going on in the real world. This is what we're trying to solve. And how do we do it? We have 3 pillars for doing this. The first, and really the foundation of everything, is having very high quality data. So we place sensors on machines, and we acquire data, we acquire raw signals at 10 kilohertz up to 140 kilohertz, depending on what we want to measure. It's not gigahertz or terahertz. Sorry about this. Then, with this raw data, we are able, and this is our main focus, to find anomalies, make sense of this raw data, whatever the shape might be. Okay? And then, once you find the anomalies, you find, well, this is something weird going on here. Go back from pointing to the time where anomaly happened, pointing to the part of the signal that's actually anomalous. And when you can do that, then you can inform an LLM model about what's going on in the machine. Now, to talk a little bit about magnetism very briefly, the core of what we do to analyze raw signals is a biomimicking approach, is to use what we call magnetic spiking neurons, which is kind of behaving like a soap bubble that you blow up, and when you keep inflating it, at some point it will burst. And this is quite similar to biological neurons, which receive information and then accumulate, have some losses, and then spike. Okay, so this is just the principle. I won't go much in the details here. So we do three things globally with our information. We measure it exactly, we convert it into spikes, so there's a conversion. Then we go through our system that's finding temporal correlations in an agnostic way, no matter what the signal is. And then we go to the layer of machine learning and LLM. Now let me show you how this works on a very simple example. Let me see if this will. Right, so it doesn't start alone. So this is our system installed on a simple coffee machine, and this is our an object that is easy to carry around, and we take it when we go to trade fairs. I couldn't take it today, it's a little bit bulky though, so I just have a movie about it. So what you will see here is how we detect when we make coffee. This is a very simple experiment. Basically, we run the machine first only empty without any capsules inside. This will be the baseline for detecting anomalies later. And then you will see what happens when we place capsules. When something new happens in the machine, how do we see it? On the top, you have a color code, which will give the output of our signal, and on the bottom, you have raw signals that are measured. Let's see if the audio as well. So you see, now the water's coming out clear. There's no capsule inside. You see signals from vibration and magnetic field. And now you have a capsule. And as you make coffee, you see an anomaly being detected. Okay, you see a color code that has been assigned like a unique fingerprint to this particular anomaly. We didn't do anything in the beginning telling the system what an anomaly would be. We just show the system what is the normal operation of the machine, normal meaning without capsule. Now you place the capsule and then you run water once and you run water second time in the same capsule. And then you can see the colors change. The contrast changes because the capsule opposes less resistance to the water flow. So then all the analog signals start becoming more similar to the case of no capsule. Okay? So this is the core principle. Now you have to imagine now that this, if it works for a coffee machine, it can work for everything, right? Maybe not. But this is what we believe. We believe that this is really agnostic and it can work on anything. I'll give you now another example from the real industrial setup. This is a plastic injection machine. If you know how plastic injection works, you have a big press, and it opens, or it closes actually with a mold inside, and plastic is being injected at very high pressure. And here in the movie, it already started, you have nothing happening until you have an anomaly at the opening of the press. You had one during injection as well. So basically, in real time, we have a baseline of how the machine should operate. This is a complex machine that doesn't work continuously. It has very sequential operation. We can learn all that. All that becomes the reference period. And then, by comparing to this reference period, we can identify anomalies. Okay? So these anomalies can be anything. Can be, in this case, for example, it was just because the machine operation was not set properly. Machine was opening too fast. The press was opening too fast, and it made a weird vibration. Okay? It can be something much worse. Besides this real-time observation, we also have a way, we also record all the data. So we keep and store absolutely all the data on a disk, and you can use this data just like a black box on an airplane. So you can have a memory of everything that ever happened in the machine. So even if something goes wrong and you miss it, you can go back and check. Here you have, for example, a view of long-term history on top, which is every line is like 10 minutes. On the bottom, you have second-by-second detailed view of what's going on, and underneath you have the raw data. Okay? And you can go in and navigate, and for each anomaly, find out what's going on. But the thing is that you don't have to do this yourself. This is done automatically by AI agents. So the only thing that you have to do is just ask questions, and everything is done underground, and you get a real answer grounded in real data. You can go and check, though. You have a window to look inside. Another example is this is a vacuum pump in the automotive industry for rubber injection. Here, our system found an anomaly about 2 years ago, I guess. It identified the anomaly, it extracted the anomalous signal, and it found that there was like 1/f noise at very low frequency and 11 hertz vibration. So what do we do with this information? We do not tell the user, imagine going to the technician and say, hey, you have 1/f noise on your machine, what's going on? You know, they're not going to do anything with it. Instead of doing this, we do everything through the same pipeline just described. And in the end, the output is reports, which are role-specific. So, for example, if you are a manager, or if you're a group leader, and this is equipment in your research facility, you get an overview of what's happening, focusing perhaps on cost, a brief overview, not more information than you needed to take a decision. If you're an engineer or a researcher and you need to have a deep dive and understand what's going on, you have a full report also describing the physical phenomena that's going on, helping you make the decision. And if you are a technician who just has to execute, then you will have a to-do list or a guidance in the execution focusing on safety as well as efficiency. Now, the good thing with this system is that it is agnostic. So at no moment in time, we tell the system what kind of signal it is receiving. It's just raw data coming at more than 10 kilohertz. That's it. So you can install it on different machines, and we did. We installed it in different industries. We have it in manufacturing mostly. Now we're going to install it in the energy sector as well as defense. So the way we see this is that if prior to the existence of this kind of systems, the information from the factory floor or from the lab was going up to the first human layer and stopping there, with this kind of system that can summarize information and collect a lot of data and make sense of it, the information can go to all the layers of the organization. So if you're a factory and you're leading and you're making decisions, then you know what's going on the factory floor. If you are a group leader or a director of a lab and you want to know how the equipment is doing, you want to know if there's any impact of your decisions on the equipment, then you can know it. Everybody receives the same information from technicians, engineers, and managers. So it can make all not only measuring and interpreting this data, but also communicating this data much more efficiently. Now, our offer is it's a full solution. So we have sensors to measure the data, a system to acquire the data, and also we have a software and the AI necessary to run the system. If you have already sensors, if you have an AI system, we can connect to that. We can use the sensors data that already exists with the condition that the data is sufficiently highly sampled. And just to close, we have a pilot program. If you want to test this technology, I think it's really affordable. We can work together. You can test it and make your own idea about how it works for you. Thank you for your attention. If you have questions, I guess we'll be.
Thank you very much. I'm pretty much interested in having coffee machines that work properly all the time, and I'm very grateful for that. But the first question will not be for you anyway. Okay, so maybe we can start by questions in the assistance if there are. So if not, I will start. Well, Philippe, you've seen that we have fabulous sources of terahertz radiation in the pepr-spin, okay? But you also have your own that apparently meet your demand. Would you see any advantage of moving to spintronic terahertz sources? And if so, what information would you need to be more interested in these solutions?
Can you hear me? Yeah. I think the main thing for us is the signal to noise in the time domain, because that's where we recover all our data from. So we get greater than 2,000, maybe even 5,000 to 1 in the time domain. So and that's the thing that resolves all our features. Not so much bandwidth. Someone was talking about bandwidth up to 10 terahertz. You lose most of that in absorption. So, for example, in the cathode and anode stuff, we're only using maybe 60 gigahertz up to 2 terahertz. So for us, that is probably the most important region of the spectrum to make sure that that has a high signal noise. I know that everyone keeps pushing. We're getting the highest bandwidth, but in the real world, once you meet a sample, all that gets lost, all that gets absorbed in the materials. And it's the lower frequency components that, even with TDS, is the important side. Saying that, at the end of the day, if you can't see your photons in the time domain, you're not going to get any data.
So in that sense, the sources that you're using nowadays are better than the ones that we would sell with the argument that they have larger bandwidths.
Yes.
Okay. So thank you for this disappointing information. There's 2 questions in the audience. Sukdeep, please.
I can hear you. So the advantage, you could think about 1.2 microns, because there you're at the zero dispersion of silica. And at the moment, what we have to do is you have to pre-compensate the pulse. The pulse propagates through, if you're at 1.5 microns, then you've got probably 30 meters of fiber. If you're at 800 nanometers, we can get to 15 meters of fiber. So it is the distance. It's the distance from the where you can put your control electronics, and that in some places that's very limited. These people have been building their sites for 50 years. We're coming along with a system in saying we want it as close as possible, but there is no room in some of these production facilities. If you go into the pharma environment, you've got to be outside room. So it is the length of fiber to the source that's going to be probably the sweet point, rather than actually what excitation wavelength or what materials you use.
Okay, thanks.
Thanks, Ziki.
Thank you. In the same range of question, can we anticipate new application using the circular polarization of terahertz? It is not well discussed in the community. In medicine or in pharmaceutics or some maybe in other kind of
well, one of the things we have to worry about all the time is, because we've got a slightly non-normal radiation, we do worry about the polarization of the pulses. So there is information there. We have toyed with doing ellipsometry many times, and that would probably be where the sweet point is. You heard people talking about epilayers today, doing QA of the epilayers. Then, yes, the polarization will be extremely important. Pharmaceutical, then you're looking at basically chirality of the materials. Yeah, we've done some work, but there's not much work that the biggest problem always is identifying the chiral materials and making sure they are really chiral materials, and that's where a lot of us have struggled with that type of work.
Please allow me to politely disagree with your remark about having no applications beyond 2 terahertz. I mean, you are talking clearly from the perspective of your clients, but I mean, there's the whole range of gas spectroscopy where you would obviously need way beyond 2 terahertz.
Yeah, you're quite correct.
And then distance monitoring of dangerous gases, fire hazards, stuff like that. I mean, there's plenty of stuff to do there, and I'm sure your competitors are doing that also.
I am totally aware that if you've got gas phase, then the absorptions go down. Most of the work that we're doing, we don't need the 5 terahertz. The 5 terahertz. It is, yes, you're right. Gas phase is probably the sweet point. We have done some work in that area, but it is a challenging area to work. So to give you an example, there's looking at explosives. But the problem with explosives is the vapor pressure is so low that you don't get a significant amount of molecules in the room for the interaction. So you have to have long path lengths. So that's yes, you're quite correct. Gas phase is an area, but we're not actively pursuing that. So
we have time for one last question. No, Matthias. You don't have the microphone. Wait for the microphone, please.
I just wanted to know, maybe I missed it, but did you mention the timing jitter of your pulses and the phase noise?
The phase noise is something that we really care about. I don't have. I mean, we have results from the units built by the laboratory, but internal results with our prototype are still to be performed. This is important because I didn't talk about all the applications that we have. One of them is using them as metrology comb for cold atoms. It's one application that we would like to investigate, and this will be the main metric to take care of. And I don't recall the first parameter you talk about. Okay. Same. I can't disclose too much about the jitter, but yeah, we have one important customer that would like to have some results regarding the jitter itself, mainly for timing distribution.
So question for Mihai then. So you did not ask it for the good coffee in the lab, but you mentioned some potential business models that you envision, I think, which are coupled to your recent EC accelerator that you want. You did not mention. I think that's an important aspect. How do you intend with the community as former member to eventually try to deploy the model that you mentioned for existing tools, to platforms? Is there something that could be an asset for you to exploit and to have good data settled?
So thank you for the question. It's a really good question. So we are looking now to find out and have as many proof of concept in as many industries as possible. And one of the places where we feel more at home is within our own community, because we left SPINTEC 3 years ago. So we would like to monitor equipment that we also know and where we can bring the added value. For example, take a sputtering chamber that has instabilities, or sometimes, like say, make a certain kind of magnetic material or some kind of film, and then for some reason one day the samples no longer work. This happens. It happened to me. It happened to my colleagues. I know it probably happened to some of you, right? Or the experiment, for some unknown reason, it doesn't work. Now, if you have something that completely measures everything that can be measured on the system, you can go back and find out what it is. You can monitor what's going on. You can monitor what the students are doing with it. If it's not used properly, you can do everything. And this is the reason why I'm addressing you, is that this is, for us, it is a big advantage of having working with equipment that we understand, where the problems that you may encounter we already know about a little bit, and where there's a good match between what we can bring and what you need.
Maybe a short question for you. So maybe to make the link with yesterday's meeting, talking about science. So you were a pioneer in spin orbitronic. Do you plan to integrate some flavor of spin orbitronics in?
For the moment, magnetic domain walls. Yeah. There's spin orbit in there, of course, because it's our flame materials.
But more, I would say more.
Perhaps. So we don't know yet. So right now we need to make a product that's on the market. So it has to be less ambitious in terms of new technology and more robust. But we're not going to stop. So this has to be continuously improving and.
Yeah, because.
Regular conventional sensors exist.
For sensing, right, this is a big issue for us, because we collect a lot of information, and we can generally analyze all this information. But what is most expensive is placing the sensors and pulling the wires. And if you can make the kind of sensors that collect high quality data with a battery for 10 years without a wire, we will definitely be interested. So this is actually what's the main bottleneck is the price of collecting information. It's no longer the price of processing or the way of processing, is how do we collect it effectively? Because if you place sensors on one place of the machine, then you know something about the machine. But once you place enough sensors, then the information that you collect has redundancy. And then you can really know for sure what's going on. And this is a non-linear gain that you have in collecting more data. But that has to be cheaper sensors. So more than better sensors, I want cheaper sensors. Wireless, if possible.
This is where maybe the connection with SpinCom will be done, hopefully.
So you may need spin torque oscillators?
Okay, thank you very much. I think it's time to finish this session.